Good day. Welcome to example 2 based on differentiability of functions. I've done example 1 in the previous video. I believe that you've watched that. If not, I encourage you to do so because this is a nice continuation from that discussion. Right. Let us take a look at this question now. Consider the function g of x, and g of x is given as a piecewise defined function, and we can see that it's two quadratic functions for restricted domains x less than or equal to 2 and x greater than 2. One of the quadratic functions have variables p and q, and that is the question. Determine the rational values of p and q if g is differentiable at x equal to 2. Remember the theorem? If a function is differentiable, then it is continuous at that particular point. So we're going to use that theorem along with the one-sided limits of differentiability to see if we can get to the values of p and q. Okay, let's go for it. So I'm going to split the board because whenever you're dealing with differentiability questions, there are at least two aspects to your solution that you need to work with. So let us deal with continuity here. Okay. Since g is differentiable, then it is continuous. Right? That means limit as x approaches 2 of g of x is equal to g of 2. Piecewise defined function. Now we need to go into our one-sided limits. Okay. Before that, let us find g of 2. G of 2, we'll find it through the first quadratic function, negative 0.5, 2 squared plus 2 times 2 plus 3. What does that give us? 5. Right? So now let's look at our limits. Limit as x approaches 2 from the left. Which function are we going to take? This one. Negative 0.5 x squared plus 2x plus 3. Okay. This will be equal to negative 0.5 2 squared plus 2 times 2 plus 3, which is indeed 5. Okay? And limit as x approaches 2 from the right, we'll take the second one now. P x squared plus qx. Sorry, just do that. Qx plus 13. Okay? This must be equal to the other one-sided limit. Okay? Which is also 5. So what is this now by substitution? P 2 squared plus q times 2 plus 13. This must be 5. So if we clean up, we have 4p plus 2q equal to negative 8. Dividing both sides by 2, we end up with 2p plus q is equal to negative 4. We're going to regard this as equation 1. So we're done with continuity, and we've generated one equation from there. Let us now go to the one-sided limit and use this fact. The function g is differentiable, so the one-sided limits of the gradient function are equal. Okay, so g is differentiable. What does that imply? Mean we have limit as x approaching 2 from the left of g prime of x is equal to limit as x approaching 2 from the right of g prime of x. Right. So we are now generating our second equation, and clearly from now you can guess, or at this point you can guess that we'll be dealing with simultaneous equations. Okay. So 2 from the left, we'll be dealing with that one. Limit x approaching 2 from the left. Find the derivative of this quadratic function. You end up with negative x plus 2. Okay. And limit as x approaching 2 from the right. Derivative of this one now will be 2px plus q. Okay. plug in here our 2, you end up with negative 2 plus 2 is equal to 2p times 2 plus q. So 0 is equal to 4p plus q, and therefore q is negative 4p. We regard this as equation 2. Okay, so we're going to substitute equation 2 into equation 1 and solve. So we now have the substitute equation 2 into equation 1. So now this becomes 2p minus 4p is equal to negative 4. Okay, so this would be negative 2p equal to negative 4, giving us p as 2. Okay, so we've got this one. What do we need now? Q, by back substitution, we go back here. Q will be negative 4 times 2. Q will be negative 8. We've answered that one as well. We've got the solution for Q as well. All right. So nice and easy. Also clean mathematics and neat mathematics. That is also an important aspect in your structure of your solution. And I believe this solution makes sense. And if you need to, you can rewatch this video to ensure that you internalize and thoroughly understand what just happened. Okay, so thank you for tuning in. I'll see you in the next set of videos as we continue our journey of mathematics. See you there.